Okay, so the first talk will be given by Professor Jinhong Yuan and Professor Ning Hai. So first, let me introduce Professor Jinhong Yuan. So Professor Jinhong Yuan received the bachelor and the PhD degree in electronics engineering from the Beijing Institute of Technology, Beijing, China. He was a research fellow with the School of Electrical Engineering at the University of Sydney, Australia. In 2000, he joined the University of Electrical Engineering and Telecommunications, University of New South Wales, Sydney, where he is currently a professor and the head of the Telecommunication Group, School of Electrical Engineering and Telecommunications. He has published 2 books, 5 book chapters, over 300 articles in telecommunications journals and conference proceedings, and 50 industrial reports. He is a co-inventor of 1 patent on MIMO systems and 2 patents on low-density parity check codes. His current research interests include error control coding and information theory, communication theory, and wireless communications. He has caused 4 Best Paper Awards and 1 Best Poster Award, including the Best Paper Award from the IEEE ICC 2018, the Best Paper Award from IEEE WCNC 2011, the Best Paper Award from the IEEE International Symposium on Wireless Communication Systems in 2007. He has served as the IEEE NSW Chapter Chair for Joint Communication Signal Processing Ocean Engineering Chapter during 2011 to 2014. He has served as an associate editor for the IEEE Transactions on Communications during 2012 to 2017. He is serving as an associate editor for the IEEE Transactions on Communications. Okay, and the other speaker is Professor Hai Ning. He received a bachelor degree from Shanghai Jiao Tong University, Shanghai, China in 1993, the master degree from University of Yokosuka, Nishihara, Japan in 2000, and a doctor degree from Osaka Prefecture University, Osaka, Japan in 2005. Since 2000, he has been a research associate with the Graduate School of Engineering, Osaka Prefecture University, where he is currently a professor. His research interests are in signal processing for communications, wireless communications, and statistical signal processing. Professor Ning was an editor of the IEEE Transactions on Wireless Communications and is currently an editor of the IEEE Transactions on Vehicle Technology. Okay, so before we start, I would like to announce the Q&A rules. So all audience, so please be muted during the seminar, and please do not annotate on your screen because your annotation gonna appear on the shared screen. So please type your questions and send them to the host or co-host. We will connect questions from room and the offsite live broadcasting, and then we're gonna ask the questions to the speaker during the Q&A sessions. Okay, the question will be named and encouraged to ask questions by themselves. Okay, so without further ado, let's welcome Professor Jinhong Yuan and Professor Ning Hai to give us an interesting talk. Okay, so I will stop my screen sharing. Hello, Professor Yuan and Professor Ning, you may start.
Jinhong, you are muted.
Professor Yuan, please unmute yourself. Professor Yuan, can you hear me?
Yes, can you hear me?
Yeah, I can hear you. Yeah, you
Good,
may,
thank you.
yeah, share your screen.
Let me share the screen. Can you see the shared screen?
Yes.
Okay, thank you, Jay, for your kind introduction. First, we would like to thank ISAC ETI for organizing this seminar and your kind invitation. It is a great initiative. It is our honor to share some of our current work and design signal waveforms for ISAC. This work actually has been done by Hai and me during the COVID lockdown for almost 2 years. It was motivated by OTFS, which has beautiful mathematics there. OTFS has inspired us to look at the channel from the delay-Doppler point of view or delay-Doppler plane and consider design transmitter and the receiver algorithms to better couple the transmitted signal with delay-Doppler domain channels. With that, we developed a new modulation waveform, which we call it delay-Doppler plane multicarrier modulation to follow the conventional way people call it multicarrier modulation signals. Or if you like, you can also call it the orthogonal delay-Doppler division multiplexing or DDM. And here we are to share some of our development with all of you here. I'm from University of New South Wales, Sydney, and Hai from Osaka Metropolitan University, Osaka, Japan. Okay, so the key of the talk is trying to introduce multi-carrier modulation, MC in DD plane. Before we talk about multi-carrier modulation, we would like to briefly overview of wireless channels or revisit how do we represent a wireless channel in different planes. And also introduce OTFS modulation, see how that motivated us to develop this multi-carrier modulation. Hopefully we have some time to left for some discussions later on. In the last 4 decades, we have seen wireless booming from 1G to 5G. Actually, we enjoy the 5G very high speed data rate transmission. The signal waveforms have been evolved from analog system to digital system, from a narrowband FDMA to narrowband TDMA to wideband CDMA, etc. And if you look at the data rate, actually we have done a lot. I mean, we means in the whole telecommunication industry. The data rate has been jumped from a kilobits per second on the first G to more than gigabits per second. You can think about it, that's 6 magnitude higher than what it was offered in the first generation system. As a physical layer researcher or engineer, what we care about is design transmitter waveforms to support high rate. And one of the difficulty for physical layer channel, for physical layer design is dealing with fading and interference, which actually is the nature of the system. We cannot get rid of, we have to deal with it, we have to coexist with this system, that is nature. And conventionally, we have a TDMA, CDMA, multi-carrier CDMA, OFDMA, and the MIMO OFDMA. You probably signal is localized the time or the frequency or spreaded like CDMA. It's neither localized in either time or frequency. So the design philosophy has been changed from the first generation, second, and third generation. In that case, we are combating channel fading. Look at it as a bad boy or bad guy to be exploiting or embracing this wireless channel fading in our 4G, 5G, which for the benefit of we utilize it to improve the capacity or the throughput of a wireless network. So that has been a lot of changes, provide a modern view of communication system design. Looking forward to the 6G, one of the important application scenario is high mobility. We will have vehicle-to-vehicle communications, high-speed rails, and up to 500 kilometers per hour. I think to provide a high reliability over this high mobility channel is not a trivial thing. I think the current 4G system, OFDM serves its purpose. It works well, but if we have a high mobility communication, we know the orthogonality between the subcarriers probably will be destroyed or affected. So how do we design system to cut with this high mobility is one of the issue. Another thing is the connected AI. I think we talk about the Internet of Things or Internet of Everything or Internet of whatever. And we will have a smart home, smart campus, smart manufacturing or remote surgery. A lot of application requires the network is able to provide both sensing capability and the communication capability. That's how bring us all to this ISAC seminar here. And the interactive, integrated sensing and communication. So one of the questions for physical layer design is there any signal waveform better interacting with wireless channels? What do we mean interacting with wireless channel means? What we mean here is the signal is able to provide a robust and reliable performance against all sorts of distortions or impairments, particularly for this AA selective channel. And more importantly, hopefully it is suitable for ISAC over these AA selective channels. In 2017, there was a seminar paper proposed by Dr. Ronnie Hadani and a bunch of famous people called OTFS. OTFs modulation gave us a new way to look at how do we transmit the signals and modulate the signal in the delay-Doppler plane, then convert it to the time frequency plane. Important issue about this modulation is it can work overlay on the existing 4G, 5G OFDM system, provide reliability over high Doppler fast fading wireless channels. In the last 5 years, a lot of work has been done to understand this new modulation and developing transceiver algorithms associated with the delay-Doppler domain signal processing and communications, such as channel estimation and the detection and the MIMO system. How do we do DD plane pre-coding? What is the security? How do we do multiple access? A lot of been done in this OTFs modulation. The key idea about OTFS modulation is to explore the underlying property of our DD domain channel, which has nice properties like compact and sparse. So if the OTF's idea is if we can carry the information in the DD domain, we are able to couple with the DD channel better. So the design aim is to try to have a full diversity provided by the DD channel. In the meantime, to have minimum cross interference. So that is the design principle for OTFS. So given conventional multi-carrier modulation, OFDM, on the right-hand side, we have a time frequency plane, this time frequency grid resources. OTFS says, let us map the signal from the DD plane to the TF plane, and your data is carried on the DD plane through a inverse symplectic finite Fourier transform. Actually, you can think about it as two pairs of Fourier transform. You map from the Doppler to time, is inverse Fourier transform, and from delay to frequency, it is a Fourier transform. So as long as you do such a mapping, you can use existing and OFDM modulation signals and to transmit your data. So OTF's waveform, as it uses OFDM underlying modulation structure, so it is orthogonal with respect to TF plane resolution. So your resolution R equal to TF equal to 1. In the initial paper, the OTFS assumes if you have bi-orthogonal robust pulses, you are able to provide a very nice property at your receiver using the existing single type equalizer as what you have in the conventional system. But the reality is such a bi-orthogonal robust pulse does not cannot be realized. So most of existing work focus on OTFs modulation with rectangular pulses. And as an engineer, we always know rectangular pulses suffer from a high out-of-band emission, which is one of the key tasks if you work on 3GPP or practical system, either for Wi-Fi, 4G, 5G system. As a result, you have a complicated ISI and ICR to deal with it. So when we talk about modulation, and we probably have to care about going back to the textbook knowledge, and each modulation probably have triplets we have to define. And the first one is we need to know and what is the information bits mapped to what kind of a signal constellation, that is signal mapping. Second one, we need to have a transmitter pulse or filters to regularize your transmitter signal spread, signal energy spread in the time and the frequency. It means you need to know what is your time and the frequency resources to be used. Third one is you need to verify, or we need to verify the time frequency lattice, means which time slot, which subcarriers you are going to use. So that is your T and the F. So that is the triplets we have to specify to design each multi-carrier modulation. Here I say, and the time and the frequency resources is regularized in practical system by the standard or by the base stations. And the pulse has to be designed before we employ the modulation. It is a fundamental element for any modulation, as we typically know, because they regularize our energy spread in the time frequency. On top of that, it is also very important to design the pulses appropriately, because the fact that our propagation and the signal characteristics also, it determines the efficiency, localization, or orthogonality of our transmitted signal. So in this talk, motivated by this OTFs modulation, we'll take a different view to look at how we are able to design DD plane multi-carrier modulation. Importantly, to answer the question, are we able to design orthogonal pulses with respect to the DD resolution? The answer is probably at the end of this talk, you probably can find it's positive. Yes, we show that there is a pulses can satisfy this requirement. And we will share with the audience colleagues here. And actually, this kind of a signal is a promising waveform for ISAC. With respect to the DD resolution, what does it come from? To answer this question, I would like to revisit the wireless channel with DD domain representation. I think for any linear time variant channel, we are able to represent it in the time delay domain, time frequency domain, or DD domain, or the Delay-Doppler domain. So this is not new, and this has been answered in our pioneer work, Bellows 1963 work, 63 paper, talk about the system of functions. There's 4 fundamental functions, 4 dual functions there. Now we just here, relevant to what we are dealing with, we probably look at, we can, as we conventional see, our channel can be represented as a time variant impulse response, HT tau. And do a Fourier transform with respect to the tau, we got the time frequency response. And we got the channel representation as the time and the frequency domain. We call the time variant transfer function, HTF. And if we do 2 pairs of Fourier transform, symplectic Fourier transform, from the time frequency domain, we are able to look at the channel in the Delay-Doppler domain. That is called the Delay-Doppler spreading function. And it tells us how many passes there, what is each pass delay, tau p, Doppler nu p, and its amplitude hp. And that has been there since a long time. But what we see from the OTFS is shows us conventional system we're dealing with the channel in the time frequency domain. We look at the time variant transfer function means that we look at the coherence region, means the coherence time, coherence bandwidth, design or communication system, regularize our frame length and the subcarrier spacing, etc. And but what we found is OTFS tells us actually we can look at the channel in the delay-Doppler spreading function, and it has nice properties which I'm going to show you next slide. But from a numeric point of view, we can take a look at a typical example. So if we have a very high speed car 120 kilometers per hour in a highway, and you can work out its coherence region, coherence time. If the car is at 5 gigahertz vehicle speed, vehicle frequency band, you can work out that the coherence time is 2.5 milliseconds typically. That means your channel, your channel Rtf remains roughly same over this coherence time. That is how you can estimate your channel and use it in your demodulation detection, etc. But if we look at the delay-Doppler spreading function, at the same frequency, if we have two cars, each at 120 kilometers over highway and running at the opposite direction, we're able to see the channel spreading function remains almost the same at 23 milliseconds. If we look at a car to a pedestrian, in that situation, the stationary time or the channel delay spreading function remains almost constant at 1.5 seconds. That means we are able to see the channel relatively stationary in that period in the delay-Doppler domain, even the channel is changing very fast in the time frequency domain. So what does that tell us? It tells us, and in time frequency domain, the channel is dense and changes quickly, difficult to perform the channel estimation. But if we look at the delay-Doppler domain, the channel is compact and stable. It actually it allows us to accurately and estimate the channel with a low overhead because we don't need to estimate the channel so often. So because the channel is relatively stationary, we can think within that stationary time, the channel is deterministic. So we can use a deterministic delay-Doppler spreading function and to represent this channel. So that is what we usually have, this path-based model. So that is a physical channel. Now we need to model that in our communication system. Now let's take a look at how Barrow and our pioneer also, Staley and Hansel, told us how do we do channel. So our real life channel and the path signals and our system has an essential finite degrees of freedom, which means that we have a finite bandwidth, we have a finite time observation period, we have to deal with our signal transmission and receiving. It turns out to be we do sampling at the receiver side. We have this sampled channel model with combined time and frequency constraint. So we have this channel model, H tau nu, is discrete or sampled channel model. And this sampled channel model has a similar representation as our physical channel. But the one difference is the delay tau p and the nu p are integers, because that is what we see at the receiver side and what we can deal with it after we sampling the system. So the delay is sampled due to your sampling rate regularized by your channel bandwidth. Doppler is sampled also with due to your Doppler resolution is due to your frame observation period of time. So we always have this integer delay and the Doppler rather than fractional delay and Doppler, what we see at the receiver side. So with this background, we are able to look at how OTFS modulation works. I hope the speed is all right. Yeah. So the OTFS modulation actually use the multi-carrier modulation as its building block. Before we do multi-carrier modulation, the signal is carried on the DD plane or DD domain. We use 2D orthogonal precode, change the signal from the DD plane or DD domain to TF domain. As long as you are in the TF domain, you can use a multicarrier modulation to change the signal to the time domain to transmit your signal through antennas. Okay, as the receiver side, you have a multi-carrier demodulation, and then you change the signal from the TF plane to the DD plane, and you do this demodulation and the decoding, etc. So this it is a very general and has very beautiful mathematics here. For example, this 2D orthogonal precode, you can use inverse symplectic finite Fourier transform, ISFT, or you can use Walsh-Hartman transforms. For this multi-carrier modulation, you can use OFDM, or you can also use field bank multi-carrier modulation. The essential point I would like to make is the OTFS reliance is the employed multi-carrier modulation waveform. So that is the key here. So for example, if we use the OFDM modulation as its underlying structure, and we have n time slots, m subcarriers, a typical scenario say for 4G, we have each frame has 14 time slots, n equal to 14, m equal to 1024 subcarriers. So that is your TF plane, okay? And so we have the total length of frame is NT. We have the total bandwidth is m delta f. That is the total, m is the number of subcarriers. So to do OTFS modulation, what we need is we need to change the signal or map the signal from the DD plane to the TF plane. So we use ISFT as the transmitter side, we use the SFFT as a receiver side. Here, what I would like to point out, this ISFT and the inverse FFT is a kind of digital sequence implementation. And they have DD plane and the TF plane has the same, actually are the same planes, just have different resolutions. How do we do demodulation? And here I borrow the slides from E and Viterbo's ICC tutorial 2019. So if we have this delay-Doppler signal, we change the signal from the delay to frequency domain, that is the inverse FFT, from a Doppler domain to the, from delay to frequency domain is FFT, from Doppler to time is inverse FFT. Then as long as we got the time frequency domain signal, we change the signal from frequency domain to the delay domain or time domain, you can call it. That is the inverse FFT. So we got the signal in time domain. So we got that the first OFDM signal, which is red, and the second OFDM is the yellow and the blue third OFDM, and the fourth OFDM signal. We stack it into a frame. Then we add a frame-wise CP at the head. So that is a typical OTFS modulation. So you can think you have n OFDM symbols, but only as the first you have this CP. At the beginning of the frame, you have the CP. And you also see this is directly implementation. You can also see, actually, you can do the signal from the delay to the frequency, that is the FFT. From frequency to delay is the inverse FFT. They cancel each other. So you can directly do the signal from the delay-Doppler to the delay and the time. So what does it mean? Means you take the signal from the Doppler, you do IFFT, directly goes the time domain signal. That is the directly implementation, or some people call it the ISAC transformation. So if we look at this directly implementation point of view, you are actually doing inverse FFT. People familiar with multi-carrier modulation or OFDM, you probably think somehow that is relevant to OFDM. Now let me redraw the same picture as what we drew before. So we have this Doppler and the delay signal, and for the first delay we have the red signal. For the second delay, we have the blue. What we are doing from the Doppler to time domain transformation is just an inverse FFT. Sorry, looks like I need to charge my battery. Okay, so we need to do an inverse FFT for the red first delay, blue second delay, and the green third delay, then stack them together. So for each one, it looks like a multi-carrier modulation, but that multi-carrier modulation is regularized from the Doppler to the time domain. For different, so we may think about that is similar to OFDM, but here is orthogonal Doppler division. For different multi-carrier modulation, for the first red one and the blue one and green one, looks like they are delay division because they have a different delay. When you stack them together, you have the right-hand side curve here. So there's a very good connection between this OTFs and the conventional OFDM, or in general, multi-carrier modulation. So motivated by this one, and we say in order to be a multi-carrier modulation, we need to have a pulse because the signal need to be helpful. So the question is, how do we design pulse? Is the pulse realizable? And what is the properties for this pulse? So with that one, I stop here. I asked my colleague Hai to talk about the important issue of pulse design. I stop sharing. Hi.
Okay. Wait a minute. Can you see it?
Yes.
Okay. Regarding the pulse design in multi-carrier modulation, we have several principles about pulse design. Basically, we need one pulse for one symbol. For example, if you want to transmit symbols, you essentially you need pulse orthogonal with each other. In practice, we usually use a prototype pulse to generate orthogonal pulse. They can be written as this function set. In this function set, we generate GMNT from GT using the time shift according to a time resolution, and frequency shift used by a frequency resolution F and tau, T and F here. So all these pulse construct a function set. On the other hand, we also have joint TF resolution, which if you are familiar with multi-carrier modulation, you can see it's called, sometimes it's called lattice areas. Okay. And another important parameter is symbol period. We have two time parameters, but be careful, the time resolution is not necessarily be the same as the symbol period. Then we can find the core of the multi-carrier modulation is to find a suitable GT given the time resolution T and the frequency solution F. For example, for CP3 OFDM, we have rectangular pulse rectangular prototype pulse to generate pulse which are orthogonal with each other. So we have symbols, and each symbols have n subcarriers. It's an example. For the prototype pulse, sometimes we call prototype filters. It's GT given T and F. And traditionally, these function sets are treated as Willy-Heisenberg or Gable function set. And to design a multi-carrier modulation, we need to find by the orthogonal or orthogonal WH or Gable set. And essentially, we need to find a prototype pulse GT given T and F. For example, the OFDM, we have a rectangular pulse for the joint TF resolution 1, when the symbol interval is the symbol period. This basic concept of pulse design can be found in these two very good tutorial papers. Now let's look at the DD plane multicarrier modulation. We recall the principle of modulation is one pulse for one symbols. In OFDM, we have a rectangular pulse here to generate the MN pulse. But for the DD plane, you see this plane, DD plane, the delay is also time. The Doppler is also frequency. So basically, the DD plane is also a TF plane, however, with high resolutions. One may think, how about we use this pulse? It's similar, we can have an orthogonal pulse. However, this tiny pulse violates the uncertainty principle, doesn't exist. So it looks like the DD plane orthogonal pulse doesn't exist. Can we find a DD plane orthogonal pulse? We call this time frequency resolutions representation in DD plane. You see, we have a frequency resolution 1 over NT, and we have a time resolution T over M. In the context of multicarrier modulation, the inverse of frequency resolution is symbol period, just as I mentioned in last slide. So this small frequency resolution means you have a long symbol period. At the same time, the small time resolution means you have a small symbol interval, which means this small interval will result the M symbols stacked with each other. The DD plane multicarrier modulation therefore looks like a type of stacked multi-tone SMT modulation. This short symbol interval indicates this signal must be wideband. However, the long symbol period in the conventional knowledge about the multicarrier modulation, the long symbol period means you are narrowband multicarrier signals. How can signal be the wideband and narrowband at the same time? So it's like look very strange. Now let's look at the implementation of the multicarrier modulation. This block diagram is a general implementation of multicarrier modulation with time windowing based transmitter. For transmit X signals, we use IDFT to generate the time domain discrete symbols. Then we use DAC to generate the transmitted symbols times the carriers. Then we multiply by the transmitted pulse to get the transmitted waveform. And finally, we time multiplication all these M symbols and send it to radio frequency. So all we need is all these things. Look, we need a very special UT here. So what's this UT? And the answer we found, this UT is a pulse chain, which is composed of N root Nyquist pulse. Each root Nyquist pulse is designed for a time interval T over M. And each root Nyquist pulse has a duration 2Q T over M. So this NAT could form a UT. The UT is the DD plane orthogonal pulse. And the ambiguity function, if you want to calculate the ambiguity function of UT, you can find the UT is a delta function on the DD plane with respect to the DD resolution. With this orthogonal pulse, we can say the DD plane multicarrier modulation as orthogonal delay-Doppler division multiplexing modulation. For example, we have N subcarriers. We have rectangular pulse for conventional OFDM. if we are doing OFDM, we have a rectangular pulse for conventional OFDM. But in ODDM, we use a different pulse to shape the subcarrier. The UT is applied to all these summation of these subcarriers. Then we have a OTDM waveform, can be written as this equation. And you can see the ODDM has a standard multicarrier modulation format where the information bearing symbols are carried by the pulse. And the pulse is orthogonal with delay and Doppler resolution. On the other hand, the OTFs, you can see the OTFs use a discrete transform, map the information bearing symbols to TF domain, then use the TF domain orthogonal pulse. Therefore, ST is orthogonal with T and 1 over T. They are two different waveforms. In the design of multicarrier modulation, we usually need to see from the degree of freedom. For example, we have a duration NT and a bandwidth M over T. According to the Loud-Park series, the degree of freedom of these signals is approximately Mn, which means we can transmit Mn symbols using this TF region. On the other hand, for the DD plane, you can see this small region only has DOF1, which means if we are limited inside this small region, we can only transmit one symbol. So it's impossible to have Mn pulse inside these small regions. With this degree of freedom, we can compare the proposed ODDM waveform with existing modulation scheme. For example, we have TDM as a single carrier. We send symbols one by one with a fixed time resolution. Also, we have FDM. We send symbols according to a frequency resolution. Also, we have a conventional OFDM. We send with a T time resolution and frequency resolution 1 over T. And finally, our proposed ODDM. It's like a 2D spreading multicarrier modulation on the TF plane. However, orthogonal with respect to the delay and Doppler resolution. Then another interesting thing is about this pulse ambiguity function, because it is orthogonal with respect to the delay and the Doppler resolution. You can find the ambiguity function. It's very interesting. For example, if we set M equals 0, we can see the this line. Okay, you have a sector here. So you can see for each Doppler resolution, you see the they are orthogonal. You only have a value here. All the integers resolution place you have 0. The same thing happens if you set the N to 0 and you check the delay resolution. It's also 0. So it's a very interesting ambiguity function. Now with this orthogonal pulse, we can easily derive the DD domain input-output relation because it's just like OFDM. So we can use the receive pulse because it's orthogonal. We can just use the receive pulse is the matched filter of the transmitted pulse. Then the pass delay is integer multiples of T over M, and the pass Doppler is integers multiples of 1 over NT. So we know OFDM with integers timing and frequency offset, you have a very special properties we can use to derive the DD domain IO relations. For example, we have a channel can be written in a matrix G. The G, the elements G, K and L represent the Doppler and delay index. Let's see from the n subcarrier of the m symbols, we can see the GKL will bring an ISAC from the n minus hat k mode Tn subcarriers of the m minus L mode M symbols. And use this relation, we can easily derive the input-output relation in DD domain, where this matrix can given in this form. And this matrix has a block circular-like structures. Jinhong, so let's move my part, please.
Okay. I'm sharing my screen. Can you see here now?
Yes.
Okay, thank you. So I probably, I think Hai has showed very good properties of this modulation, but there's no free lunch. And it looks like everything is quite good, except we see, let me show this one. And we cannot use the conventional OFDM and single tap equalizer because the channel has this delay and Doppler interference introduced merely by the channel. It's not by signal itself. We had to be, so how do we do detection? That is one issue we have to conquer. So there's existing work. People have been talk about all sorts of detection algorithm or equalization algorithms. For example, we can use map detection, but the complexity is to the exponential to the signal cancellation size to the Mn. Mn represents the number of time slots and the number of subcarriers. Or if we use MMSE, it is Mn to the power of 3. Or we can use the message passing, and that is linearly to Mn, also to the number of passes and to the cancellation size. Or we can slightly tweak the transmitted signal. So say, let us say DD domain multicarrier modulation with 0 padding. We can use some low complexity MRC-SIC, means maximum ratio combining successive interference cancellation, or MMSE-SIC. And the complexity for MRC is MN L. L is the number of passes, or it is MN L to the power of 3 to MMSE. So that's just manageable from our point of view. So particularly say, if you do MMSE, how do you do it? So you detect the first group of signal by using this matrix. Then you remove the interference from X. You detect X0. You remove the interference. Then you do detect X1, then etc. So with that one, I think the performance, the complexity can, and the performance has a good trade-off. Now we are going to show you some results, just 2 results. First one is we show what is the difference between OTFS and the Oddm in terms of their power spectrum density. And you see this OTFS red one has a severe out of band emission, and Oddm we use raw factor 0.25. Obviously, you have slightly increased bandwidth, but your OBE is matched quite low, more than 20 dB lower than the OTFS. And we also evaluate the beta rate performance for OTFS and Oddm for different speed. You see they both robust to the Doppler shift. But one thing we can see is that at a high signal to noise ratio, Oddm has a kind of 2 dB performance gain over the OTFS. Okay, so the parameter for this system is for the EVA channel at the carrier frequency 5 gigahertz and etc. You will see here. With that one, I would like to summarize the talk with these 2 nice figures. It's like basically motivated by OTFS, we have shown an example of design practical signal waveforms. And in our personal view, this signal waveform, a multi-carrier delay-Doppler plane, has a very nice property. One property is you can see in the in terms of our communication system, and our signal is distributed over the time frequency domain. And how do you see the picture? I mean, the same color representing the same modulated signal situated or distributed. And you can see the signal is distributed over the time and over the frequency. Obviously, you have a time selective fading channel, you are able to explore the frequency diversity. Also, you can have the time diversity on the other around. So this is quite new from our point of view. That's interesting. From a sensing point of view, and as far as we understand, the sensing, people care about the ambiguity function, but because that tells you how accurate you are able to estimate your target speed and the distance, etc. And we saw this orthogonality with respect to the delay and the Doppler is quite nice. People would like to have. So fits the ISAC perspective. So we say it's a nice property, like we have a new modulation, embrace the DD channel property. We have designed the DD plane orthogonal pulse and has potential to provide a high reliability in terms of communication system or good accuracy for sensing system. There are still many open questions, probably we may have in our minds. For example, it does not, I mean, the current design, we show an example, but if you look at it carefully, it does not fit in the existing WH frame-based pulse design principle. So from a theoretical point of view, is there any theory we can explore or develop? We don't know yet. And what is the achievable rate for this ODDM? And can we further reduce the detection capability or complexity? How to explore the properties to meet the sensing objectives? And how do you work with multiple user system? And how do you do resource allocation? And how do you work with MIMO system? And latency probably is an issue. So I think there's quite a lot of other issues, but with that one, we stop here and hope this could intrigue researchers for future development. So the main result is publishing our ICC paper and also trans wireless communication to appear. Here, I would like to particularly thank the ISAC special interest group for the invitation, and thank everyone online to listen to the talk, and also thank our founding bodies and industry partners, particularly our great students, postdocs who contributed to the discussion. We also take the chance to say we have postdoc position, existing postdoc positions in this domain. If you are interested, please contact us. Thank you very much, everyone.
Okay, thank you very much, Professor Yuan and Professor Lin. So I got a couple of questions. So now I would like to ask the speakers. So this one question from Professor Andrew Zhang. Okay, the question is, could you please explain intuitively what is the performance gain of ODDM compared to OTFS? Is it because a reduced ISI with the use of orthogonal pulses, but the signal and the channel in the DD domain is a conventional relationship? How the orthogonality improves such a relationship at the receiver?
Okay, very good question. If we could answer briefly, say, in terms of communication system, this is ODDM and have exactly input-output relation, because when you look at the input-output relation, the signal itself is orthogonal with itself. So whenever you have ISI, that is introduced by the channel. So we're able to use this information specifically in this detection when we use method busing algorithm. But for OTFS, you probably use approximate input-output relation, and because your signal is orthogonal with time frequency, but not the delay Doppler. So you have some approximations. That approximation introduce performance degradations here. Hai, would you like to add something, or that's?
I think it's you answer the questions. It's fine.
Yeah. Thank you.
Okay, thanks. So this is another question from Professor Zilong Liu. And the question is, if we ignore the implementation complexity or backwards compatibility, so are you aware of any pre-coding schemes other than OTFS, which are more effective for certain wireless channels?
Very good question. I think there is a paper. Let me try to answer this first and see how I can add something. And there's a paper talking about, if I go back here, OTFS. There's a paper, I think there are a couple of papers talking about how you do pre-coding. And it's by Zeman's paper. I don't think we cited here, but you can find it later. And they say, as long as you do orthogonal pre-coding here, and you probably achieve the same performance because they are all pre-coding based. They say this OTFS can be considered as a pre-coded OFDM system. So as long as it's orthogonal pre-coding, you probably achieve the same performance. And that is my understanding. And Hai, would you like to add something, or?
Yes, I think the paper is Dr. Zeman published in 2018 PIMRC. Yeah.
Okay, thanks for the excellent answer. And this other question from Ahmed Bazi. And the question is, why are the multipass components always assumed to be on the G grade or integer multiples? So could they lie in between or not? And okay. Is this like a compressive sensing type approximation? So that's a question.
Okay, very good question. I think in the literature, let me try to answer this one first and see how I want to add something. In the literature, we always say fractional delay and fractional Doppler. I think there could be some concept to be clarified. I would say this: in physical channel, your delay and the Doppler. If we look at this one, the path-based model, there's the tiered tau p and the tiered nu p are all any real numbers. And so they could be any number. There's no grade and for time and frequency or delay Doppler at all, because this is exactly physical channel. But what Bellow and Stella Hansel tells us, whenever at the receiver side, we observe the channel due to we have the limited degree of freedom, basically limited bandwidth and the limited what is called time duration for us to do the signal processing. And we do sampling. After sample, all those off-grid passes will be combined or not combined, somehow combined. And what we see is their combined version on the grid. So for this model we show here is what we see. It is what we model the real physical channel. But what we see is this tau p and the nu p are on the grid. This model, two different model. One is a real model, another is a modeled, sampled channel model. So whenever we sample this channel model, it is on the grid. Yeah, that is not saying your physical channel is on the grid. Okay, that is the point I would like to make. Hopefully it is clear.
Yes, thank you very much. Thank you. And very interesting talk, by the way.
Okay, thank you.
Okay, so due to time limitation, maybe I will have a final question. So the question is from Jinhong. Okay, so the question is regarding the effective channel in the digital domain. So the question is, could we expect that the ODDM will see a much sparser channel as compared to the OTFS?
Let me see. What do you mean? I think they should. I think we should have the same channel drain, and because if we look at this, modeled channel, this modeled channel only consider and your physical channel after we do sampling. If we do the sampling with same bandwidth, that means we have the same delay resolution. We have the same frame size, that means we have the same Doppler resolution. We will see the same channel.
Sorry, I just want to add a word.
Yeah, please.
This kind of channel delay resolution depends on your receiver filter. So yeah. After the receiver filter, you do resampling. So you see the equivalent channel is a combination of the transmitter filter, physical channel, and the receiver filter. So if you use different filter, they may cause a different equivalent channel.
ODDM 我就听不太懂了，我再跑学。
So that's my answer to your questions. If you use different filter, you see different channel. But
okay.
Eventually,
thank you very much.
You will see the on the grid channel because you are performing sampling.
Yeah.
Thanks a lot.
Okay. Oh, okay. Thanks for the answer. And we still get several questions, but due to that limitation, maybe we do not have time to ask the speakers during the seminar. So if you have any further question, maybe you can drop email to Professor Yuan and Professor Lin. Okay. So thank you very much, Professor Yuan and Professor Lin. Thanks for the interesting talk.
Thank you.
Okay, thank you very much. Yeah, we would be happy to answer the questions by email. Bye.